Hi, I'm Roger Hamilarin and I'll be presenting our proposed method of generating higher order Bessel beams or hubs by spiral slits using digital micromirror device. Hubs are among optical vortex beams that possess orbital angular momentum, quantified by topological charge L. A non-zero value of L implies that the beam has a helical phase, resulting to singularity on its propagation axis. In effect, a point of zero intensity we will call the central dark core will be observed on the transverse profile of the beam. Hubs were widely used because aside from that they can carry momentum, they are also non-diffracting and self-healing. Applications such as optical micromanipulation and free space communication exploit these properties of such beams. This demands to more ways to generate hubs. Lately, Young et al. Devised a diffraction setup to generate these beams utilizing a spatial light modulator or SLM as a spiral slit, modeled from Fermat's spiral. While SLMs allowed fast switching rate to various slits, using an SLM made their setup dependent to the polarization of incident beam, and better alternative is proposed. Instead of an SLM, we use digital micromirror device or DMD as our spiral slit, retaining switching rate and beam fidelity while being cost effective. Like an SLM, we can also adjust the spiral slit's width and extent through the DMD. The spiral width is adjusted to optimize the morphology of the transverse profile of the beam, minimizing the contribution of the geometric waves and so the effects of interference. Then, we adjust the spiral slit's extent to generate hubs for a specific range of L. We observe the central dark core for non-zero values of L, which increases in size as L increases. This implies that hubs with larger central dark core possibly have higher OM content. We would like to thank DOST-SCI and SPP 2020. Thank you for watching.
Good day, everyone. I am Sarah Pasukat, and I will be presenting our work on modified Strehl ratio for quantitative evaluation of speckle development. Fully developed speckled patterns are observed when a rough object causes an incident coherent light to form a random intensity distribution. Partially developed speckled patterns, however, contain an additional unperturbed component to the scattering. Although partially developed speckles have theoretical and practical importance, they are not fully exploited because there are limited suitable diffusers. The Strehl ratio is an evaluation method that uses the highest intensity at the focal point of wavelengths to measure the image formation quality of lens-based systems, but it has not been applied in conjunction with speckled patterns. So in this study, we demonstrate a characterization method of speckled pattern development based on a modified Strehl ratio. The method simply compares the average intensity of the area of a speckled pattern to the average intensity of the center area of the same speckled pattern. The Strehl ratio calculation is repeated as the area with the average intensity from the center moves across from the center per iteration to obtain a speckled pattern profile. Partially developed speckles are characterized to have decreasing Strehl profiles, which stabilize to indicate the difference in intensity distribution between the unperturbed and scattering component. When the depth of a diffuser is greater than or equal to 2 pi, the beam becomes completely scattered and the unperturbed component cannot be observed. Therefore, the Strehl ratio values increase and the slope of the profile decreases until the spectral pattern fully develops. This shows that the modified Strehl method is a simple and robust way to quantify the development of speckled patterns based on intensity, and it could be applied in fabrication diffusers with various spectral development. Here are our references, and thank you very much.
Good day, everyone. I am Jared Operana, and I will be presenting our paper entitled An Approach to Thin Film Oxide Detection in Gallium Arsenide Substrates Using Goos-Hanchen Shift. When gallium arsenide substrates are exposed to room conditions, it promotes the growth of an unwanted oxide. This can induce bad deposition growth, lowering its overall quality. Using an atomic force microscope is one way of gauging the oxide thickness in the substrate. Downside to this is the need for the substrate to be analyzed before the formation of oxides, which can increase the tediousness of the detection. So how can we make the detection more straightforward? Here is where the paper attempts to employ the concept of Goos-Hanchen shift as the method for detecting the oxide. The key factor here is that the reflecting material affects the reflected beam's deviation. Here we can see that the application of the GH shift method simplifies the oxide detection. We can use two separate samples to compare the resulting Goos-Hanchen shift of the reflected light. By varying the angle of incidence, the amount of shift can be obtained in each respective angle. For our numerical calculation purposes, the gallium arsenide substrate is assumed to be greater than 100 microns, while the thickness of the oxide is around 4 nanometers. For the results, it might seem at a first glance that there is negligible difference between the two systems. However, when we superimpose the results, the difference becomes apparent. In addition, we can see from these results that we can obtain decreasing amounts of shift when the beam waist of the incident beam is decreased. But for both systems, we can see that the differences in shift is in the order of 10 to the negative 5 meters. Since the differences in shifts accounted for are within the resolution of Goos-Hanchen shift measurement, the viability of Goos-Hanchen shift measurement in detecting thin film oxides in gallium arsenide substrates was demonstrated. These findings suggest extending the GH shift method in detecting thin film oxides in other substrates as well. That concludes my presentation, and if anyone wants to see our paper, the QR code is provided below. Thank you for listening.
Hello, good day. I'm Joshua Lorenzo from NIPUP Diliman, and I will be presenting our work on a new method for the quantitative analysis of self-healing for structured light beams. Self-healing is a property of certain structured light beams to reform their intensity profile even after a partial obstruction. Whereas a regular beam will be almost totally blocked, a self-healing beam is able to recover its features after some propagation distance. While qualitative observations about self-healing may be simple, actual quantitative measurements are difficult. Previous methods each have their weaknesses which limit their applicability. Our method works to subvert these limitations by taking a look at how the energy of the beam flows when it self-heals. We make use of the Poynting vector, which describes the magnitude and the direction of the energy flow in electromagnetic waves. In a physical beam of light, the Poynting vector can be expressed in terms of a longitudinal component, S sub z, and the transverse component. The two components are expressed as follows, with both components only needing information regarding the profile of the beam's electric field. By using the expression for the transverse Poynting vector, we are able to quantify how the transverse profile of the beam evolves at each particular point. By implementing this method to obstructed beams, the magnitude of the transverse Poynting vector indicates the rate of self-healing at the blocked area. We are also able to identify the location and direction of energy flow responsible for the reconstruction. Finally, the method allows for quantitative comparison between the self-healing capability of different types of beams. Thank you. You may reach us at this email address. The manuscript PDF is also available at the link below. Thank you again.
We want our devices to come in small sizes, which is why the physical realization of 2D atomic crystals such as graphene and hexagonal boron nitride attracted the interest of many scientists. These 2D materials are now being used in electronic devices such as transistors and LEDs. Graphene, being conducting, can absorb light, which enables it to be visible on a substrate. On the other hand, the hexagonal boron nitride is non-conducting, that gives it a very low visibility even on oxidized substrates. In this study, we discuss how the angle of incidence of light can improve the visibility of a hexagonal boron nitride. We consider two models for a monolayer boron nitride: the thin film model or the slab model, and the perfect sheet model or the infinitesimally thin sheet model. Our calculation shows that the visibility of boron nitride is improved when the incident light shines onto the sample at the substrate's pseudo-Brewster angle. We observe that the two different models predict different spectral visibility curves for oblique incident angles. With this, we can say that the visibility measurement at the pseudo-Brewster incidence can tell us the nature of a monolayer boron nitride, whether it is a slab or a perfect sheet. For more info, you can scan this QR code or you can contact me through the following platforms. Thank you for your time.
Good day, everyone. I am Jelly P. Gloria, and I will be presenting to you a model for phase retrieval under partially coherent illumination. During intensity recording, conventional phase retrieval method use coherent light sources like lasers. However, their coherence requirement restricts the use of phase retrieval itself as well as the range of its application. So, we demonstrate phase retrieval using the properties of partially coherent illumination beam numerically. We used 500 realizations of complex transmittance screen made by complex Gaussian random numbers for the GSM beam as the partially coherent type. Subsequently, we used an ordered SP mirror to retrieve the phase from 12 different recorded intensities. The figures show the generated GSM beam using 0.5 mm beam width and 0.6 mm coherence length. Although we can see the differences of the phases in figures C and D, this would be negligible if we compare the values from the color bars. After 7 iterations of USB mirror, we were able to obtain similar amplitude and phase of the object. We can infer that phase retrieval using GSM beam is possible. We also tried changing the coherence length of the source and iterated them 7 times. Artifacts were seen for both cases. Furthermore, the graph of the phase RMSE versus the number of iterations tells us that two cases need more than 10 iterations to reach the stopping criterion. In conclusion, we were able to synthesize GSM beam and use it for the phase retrieval algorithm. As an outlook, we could use other types of partially coherent beam models to further explore constraints on the phase retrieval algorithm and also experimentally validate the numerical model. Thank you.
Good day, everyone. I'm Agatha Jill D. Manso, and today I'll be presenting the research entitled Phase Retrieval of Test Objects with Unknown Obstructions using Unordered Propagations. So optical detection devices can only record the intensity of a light wave, which is related to its amplitude, and they do not allow the direct recording of the phase. So phase retrieval algorithms have been a field of interest to recover the phase and reconstruct the wavefront. It provides advantage since no reference wave is required and it has applications in numerous fields. However, obstructions may cause the divergence of the iterative algorithm, so we investigate the performance of the unordered propagations with different parameters. For the setup, we use a helium-neon laser, and a CCD camera records the intensity at multiple planes. The obstruction is at different distances indicated in the results. Instead of using the sequential propagation, we use the unordered propagation, with the RS wave propagation from one plane to another. In the simulations, we use an aperture object with a spherical face, and the obstruction is an amplitude type object. In this figure, the results show the reconstruction with obstruction at varying distances. So with no obstruction, USB mirror showed faster convergence than the conventional SB mirror. And obstructions near the object blocks the part at the object wave in its location, so it affects the reconstruction. So we see the obvious presence of obstruction, and still the USB mirror has faster convergence. Also, at increasing iterations, better reconstruction are observed. So here we show that the USB mirror still has faster convergence than the conventional one, even in the presence of obstruction, and at relatively far distances of obstruction, we show better wavefront reconstruction, which also depends on the properties of the objects and the obstruction. That's all, thank you.
Good day. I am Rigel Tabuzo, and I will talk about enhanced reconstruction and mass translation phase retrieval using two recording planes. Wavefronts are conventionally captured as intensities only. Solutions to retrieve important phase information include the single beam multiple intensity reconstruction, or SP mirror. Its drawback is requiring mechanical translations off the sensor. In this study, we retrieve wavefronts by generating intensity variation through an in-plane translating phase mask and spatially separated recordings. The techniques use a beam splitter to capture intensities at two planes. The known phase mask shifts by 1 pixel to create multiple states. These eradicate the need for moving recording parts. SBMR iteratively propagates wavefronts, beginning with the guess U0 brought to CCD1 and updated with the square root of the intensity of the corresponding recording. The new wavefront is brought to CCD2 and updated accordingly. Then these steps are implemented in reverse and capped with the demodulation of the wavefront using the known phase mask. For the specific initializations in figures 1A and E, the algorithm required at least 8 recordings to reconstruct the phase figure 1G. The convergence in the error plot also supports this result. We looked into phase depth, which is the range of values in the phase distribution. We found that a minimum of 0.45 pi leads to reconstruction. Below this, the algorithm stagnates as in figure 2F. The technique's limitations are set by the test object, requiring unique parameters for reconstruction. We have shown a 2-plane phase retrieval technique using a translating phase mask, doubling data collection in a short amount of time. 8 recordings and a phase depth of 0.45 pi enable reconstruction for the chosen test object. Extensions include the use of phase type objects and unknown phase masks. We thank Fu Saizang for valuable discussion. Thank you for your attention.
The concept of quantum entanglement has long been a prominent topic in the field of quantum mechanics. The phenomenon explains that when 2 particles are entangled, measurements made on one particle would dictate the state of the other particle. Now, introducing a similar concept to one classical system, we have vector vortex beams. Vector vortex beams are states of light where the spatial modes and the polarization modes are described to be classically entangled or non-separable. Intuitively, this non-separability poses an important question. Can we control one state by changing the other state? For instance, can we detect the polarization state by changing the spatial mode? This is significant because if this is actually possible, we can determine the chirality of a certain medium, which is useful in spectroscopy and biophotonics. And these are the questions we explore in our paper. To show that we can detect the spatial modes, what we do is we project the equation for the vector vortex beam onto a polarizer. This is similarly calculated to detect the polarization modes, where the beam is projected onto a digital micromirror device, and we get the resulting beam. Now, the resulting intensities of the projected beams show that we can control the degree of non-separability between the 2 modes. Thus, the calculations imply that we can project the vector vortex beam onto any of the 2 modes, and the observed intensity can be used to quantify based on the weighted term. So, going back to our question, can we control one state by changing the other state? In our study, we show that mathematically, yes, we can. Thank you for listening. If you want to know more about our work, please check the SPP website and search for our code 3G-10. Thank you.